All right, hello there. This is Ms. Page, and this lesson is going to be about how we solve what are called logarithmic equations. Logarithmic equations are equations that involve logarithms where the variable is either part of the argument or it is a base value. We're going to focus on problems where the variable is part of an argument, which is a more common type of problem for this lesson. One of the things that we will need to use is our properties of logarithms, which we learned about in a previous lesson. And so that we can actually get to one of the two forms that are necessary towards being able to move forward with the problem. And so remember that if we're going to use our properties of logarithms, that they have an order of operations as well as like when we do basic calculations. So if we have to, we would first use our power property of logarithms. So if we have any expression like this, we're going to rewrite it like that. Then we would use the product and or quotient, and they're a left to right rule, remember. So what's going to happen is if we have a sum or a difference of two logarithms on one side, we're going to rewrite it as a single logarithm. And then if we have, at this point, after using these properties of logarithms, if we have this structure, a logarithm of a certain base equals another logarithm of that same base, then we'll use this property of equality for logarithms, which says, well, then our arguments would have to be equal, and our variable will be somewhere in one or both of those arguments. If, however, we end up with this structure, we have a single logarithm equals a number, then we'll recognize, well, logarithms are equal to exponents, so that number is our exponent. We'll rewrite it in our exponential form and continue from here. So we will use one of these in the third step, depending on what form or structure we have. All right, so this is just kind of outlining what I was just talking about, but it does add a very important thing we need to keep in mind when solving logarithmic equations, and that is extraneous solutions. Because remember that if our variable is part of the argument, arguments have to be positive quantities, greater than 0. So if you get any solution for your variable that creates an argument that would be equal to 0 or a negative number, then it is not going to be valid, and we're going to have to throw it out. All right, let's take a look at this problem here. So this is a type of logarithmic equation. This one involves natural logarithms. And so the basic property or procedure is the same, regardless of what type of logarithm is in the equation. We want to go through and use all properties of logarithms first, following the order of operations for them, and then use algebra to continue, and then check our solutions to make sure that they're valid. So the first thing I want to do is look to see if I need to use the power property. So as we've learned, we want to scan the problem looking in front of each logarithm for a multiplying factor other than 1. And every single place we find that, we are going to use our power property and pull those to the exponent positions on the arguments. So that means we're now going to have the natural logarithm of x squared equals the natural logarithm of 2 to the 6th power minus the natural logarithm of 2 to the 4th power. So now what I have, simplifying each of these arguments, because those are equal to numbers, so I have natural logarithm of x squared equals the natural logarithm of 64 minus the natural logarithm of 16. At this point, I look to see if I have a sum or difference of two logarithms on the same side of the equation, in which I have a difference here. So that means that I now want to combine those into one new logarithm using the quotient property. So the quotient property says that these will become one new natural logarithm with an argument that's the quotient of the first divided by the second argument. So I have 64 divided by 16. I would also simplify this as much as possible. In this case, that gives me the natural logarithm of 4. At this point, I now have to recognize I'm done with my properties, and my structure tells me where I go next. Which of these strategies I now use? In our case, what we have is a natural logarithm equals a natural logarithm. So we're going to use this property of equality for logarithms that says the arguments must then be the same. So third step will be property of equality. And so this argument of x squared must be equal to this argument of 4. So from here, it's basic algebra. Square root property gives me x equals plus or minus the square root of 4, which gives me two possible solutions, -2 and +2. Each one of these I want to check to see if they are valid or not. So I go back to the original equation. Super important that we use the original equation for this process, because if we use this first step, we will actually get the wrong conclusion. Because with -2, plugging it into the original equation creates the natural logarithm of -2, which is invalid because our argument would be negative. If we mistakenly use this structure, -2 squared is +4, and that would have been fine because the final result would have been a positive argument. So we have to realize the original equation is what we must check in. So in this case, our -2 is not valid, but 2 is fine because plugging into the original, we get the natural logarithm of 2, and that argument is positive. So our final solution will be that x is equal to 2. All right. Let's take a look at this one. So again, analyzing the structure of the original logarithmic equation is super important to realize what needs to be done and also what doesn't need to be done. This particular equation, we need to recognize that its structure is actually a logarithm of base 2 equals a logarithm of base 2. And so no properties would be needed for this particular problem, because what we can actually start with is our property of equality. Because if we have a logarithm of base 2 equals another logarithm of base 2, this argument of x squared minus 2 must be equal to that argument of 10. So we have x squared minus 2 equals 10. And we continue from here using our algebra. Adding 2 gives us x squared equals 12. Again, using our square root property, we get x equals plus or minus the square root of 12, which I would simplify to a -2 root 3 and a +2 root 3. And then I would check each of these to determine whether they are valid or not. Now, in this case, my original equation again is what I want to use. I would probably use the square root of the positive and negative square root of 12 for my check, but I'm not really caring about the math. I'm caring about whether it's going to be a positive or a negative. So what I notice here is if I were to take my negative square root of 12 and square it, well, that means a negative times a negative, which is a positive. And the square and square root would cancel. That gives me positive 12. And 12 minus 2 is positive 10. And so it's absolutely, the negative this time is absolutely fine because of the structure of the original equation. It creates a positive argument for both the -2 root 3 and the +2 root 3. So they're both fine, and I keep them both. All right. Let's try this practice problem. All right, so for this practice problem, as you can see here, it's done in 3 different ways. This one uses the original equation and the quotient property with the subtraction. This one actually adds the natural logarithm of x squared to both sides and then uses the product property of logarithms to rewrite this as the natural logarithm of 2x squared, then the equality property, and from there. This one right here adds the natural logarithm of x squared to both sides and subtracts the natural logarithm of 2 from both sides, and then uses the quotient property, the equality property, and algebra. All right, we're going to move on to the next example now. Let's take a look at this one. All right, so again, using my properties of logarithms to combine, first thing, I look to see if there's a multiplier in front of any logarithm that's other than 1, and here I find a 2. So that means I must right now use the power property and pull that multiplier to the exponent position. So that's going to make log base 6 of 2 squared, which is 4. Next, I'm looking to see, do I need to use product or quotient properties? And I have a sum of 2 logarithms on each side. So I'm going to use the product property on both the left and the right sides of this equation. So the product property will rewrite these two as one new logarithm of base 6 with an argument that's the product of these two binomials. So I'm just going to do that multiplication here, x squared plus 2x minus 8. And this, the product property, will rewrite these two logarithms as one logarithm of base 6 with a new argument that's the product of 4 and x, so I get 4x. So now my structure is a logarithm of base 6 equals another logarithm of base 6. So now my equality property, or property of equality, says that the first argument must be equal to the second argument. So x squared plus 2x minus 8 must be equal to 4x. So this time I have a quadratic equation that I need to solve, so I'm going to get it into standard form. If I can factor it, I will, because that'll probably be a little faster. If not, I could use my quadratic formula. Here I get factors of x minus 4 and x plus 2. And so my zero product property gives me possible solutions of positive 4 and negative 2. So now I have to check each of these to see what they do with the original arguments. So looking at my positive 4, here I'd have an argument of 4 plus 4, which would be 8. 8's greater than 0, I'm good there. Here I'd have 4 minus 2, that is 2, which is greater than 0, so I'm good there. And here it would just give me an argument of 4, which 4 being greater than 0, it's good there. So I'm good with 4. Negative 2 seems to be okay at first, because here negative 2 plus 4 is positive 2, so that's good. But in each of these other arguments, it doesn't work so well. Negative 2 minus 2 gives me an argument of negative 4, and over here I'd have an argument of negative 2, so it's gone. And my only valid solution then is positive 4. All right, let's try this practice problem. All right, so here in this practice problem, hopefully you came up with the conclusion of no solution. Both of our possible solutions aren't valid. 3 actually creates an argument of 0, which is not a positive number, so it's not valid, and negative 1 creates at least one negative argument. All right, let's take a look at this next problem. All right, so in this one again, I am first scanning to see if I need to use the power property. So I'm looking for multiplying factors of other numbers than 1 in front of my logarithms. Here I don't have that, so I don't need to do that. I do find subtraction here, and that allows me then as my first step to use the quotient property. Now I do have the option of adding this logarithm to both sides and turning it into a plus over here. That is an option. For this particular example though, I'm going to use the quotient property so that the structure of the algebra is clear to everyone. So if in a situation this is what you have to do, because there are problems where there isn't an option and you end up having to use your quotient property, then you can handle the algebra correctly. So the quotient property would allow us to rewrite these two logarithms as a new logarithm of base 3 with an argument that is the quotient of these two. It has to be the first argument divided by the second. So that gives us 2x divided by x minus 3, and that's equal to the logarithm base 3 of 5. So now my property of equality, because I have a logarithm base 3 equals another logarithm base 3, says that this first argument must be equal to this second argument. So now I have 2x divided by x minus 3 equals 5. So now my algebra here, I need to get to the point where I have x equals, and there's no way to simplify this quotient any further than what it is. So what I have to do is undo this division and multiply both sides by x minus 3. And over here, my structure is a monomial times a binomial, so I must, of course, distribute. And over here, x minus 3 divided by itself reduces to 1, and I have 1 times 2x, which is 2x. So we now have 2x equals 5x minus 15. Then I would probably subtract 2x and add 15 to both sides so that things stay positive. You could also just subtract 5x from both sides, your choice. If I subtract the 2x and add the 15, I get 15 equals 3x, and then dividing by 3, I get a possible solution of 5. So now I have to check it. And so I check here, 2 times 5 is 10, which is positive, so I'm good there. I also have to check here, 5 minus 3 is positive 2, so I'm good there. So x equals 5 is a valid solution. All right, let's take a look at this next practice problem. All right, so for this one, hopefully you came up with a solution of 1/4. Here's another practice problem. All right, so in this next example, we are going to be solving this logarithmic equation. And this one, hopefully you notice, has a different structure from the ones that we looked at previously. We do have logarithms, but we only have logarithms on one side, or you can think we have a number that is not a logarithm. That's actually the key thing that we need to be aware of here. So the structure that we need is a logarithm equals a number, which is actually the structure that we have. So we don't have to use any properties of logarithms in this particular problem. What we need to recognize is our structure here and be able to rewrite this in exponential form. And that requires, of course, that we know the base of our natural logarithm. So our base of that is e. So we know that our natural logarithm is a logarithm of base e. So that's our base of our power. We know that what a logarithm is equal to is our exponent value. And then our argument is what the power is equal to, the value of the power. So our exponential form would be e to the 6th power equals 2x minus 1. Now we're not using a calculator here, so something like e to the 6th power, which is a very large irrational number, we're just going to leave it in this power form, and we're going to continue using our basic algebra to solve for x. So we'd add 1 to both sides. So now what we have is e to the 6th power plus 1 equals 2x. Then we would divide both sides by 2, and so our x becomes e to the 6th power plus 1, excuse me, all divided by 2. Now, we do have to check to determine if this is actually a valid solution. And this one actually requires some number sense. So what we have here, so what our number sense has to tell us, so we know e is about 2.7. So it's not quite 3, but 3 to the 6th power we know is going to be a very large number. So e to the 6th power is going to be a very large number. Plus 1 and divided by 2, it's still going to be a very large positive number. So plugging it back into x in our argument, 2 times that very large number minus 1, we should recognize is going to be a positive argument value. So that tells us, okay, this is going to be a valid solution for this equation. All right, let's take a look at our next example. So here we have similar type of structure. So we have a logarithm equals a number, and so there's no need here to use any properties of logarithms. We've already got it as simplified as we could possibly get it before moving on to the point to where we change this now into its exponential form. So here we have to recognize this is our common logarithm expression. So that means we have a logarithm of base 10. So the base of our power is 10. We know logarithms are equal to an exponent value, so that would be our 2, the exponent. And then the argument of 3x plus 1 is what our power would be equal to. So our exponential form becomes 10 squared must be equal to 3x plus 1. This now allows us to use basic math and basic algebra to solve for x. So 10 squared is 100. And then I would subtract 1 from both sides, giving me 3x equals 99. And then dividing both sides by 3 will give me an x value of 33. Again, I have to check to see if this is a valid solution or not. So I'm plugging my 33 back into x for my argument, doing some math here, and that's going to give me 100, which is a positive number. Arguments need to be positive, so it's fine. It checks. All right, let's take a look at a third example of this particular type. So here we notice we do have a number that's not a logarithm. But we also have an expression over here that involves the difference of 2 logarithms. So in this case, we're going to need to use some properties of logarithms, or a property of logarithms first. We don't need the power property because our multipliers in front of each of our logarithms are 1s. We don't have to worry about that then. But the difference here means I am going to want to use the quotient property first. So the quotient property of logarithms we've learned says we can rewrite this difference as a new logarithm of base 2, but the new argument will have to be the quotient or division of the original arguments. And remember, it has to be the first argument divided by the second. So it becomes x plus 5 divided by 6, and that equals 3. Now what I have here is my single logarithm equals a number, and when I get this structure, that is when I use my exponential form. So this time I have a base 2 logarithm, and the number my logarithm is equal to, that's my exponent, and so I have 2 to the 3rd power must be equal to this argument value of x plus 5 over 6. So I would use my basic math, simplify 2 cubed, which would be 8. And then I would start using my basic undoing algebra. What I need to undo first here, though, because the addition is in the numerator of this ratio, I actually have to undo this division. There are unwritten parentheses around that x plus 5. So I must undo the division first. So multiply both sides by 6, so I get 48. And then I can undo the addition and subtract, giving me an x value of 43. As with all logarithmic equations, I now have to check to see if this is a valid solution. So I look at what happens when I plug in the 43 for x and make sure that I get positive arguments. If I don't, then I have to throw it out as a solution that's not valid. But 43 plus 5 is 48, which is positive, so that means that it will be perfectly acceptable as a solution. All right, let's try this practice problem. All right, so hopefully you came up with a valid solution of e to the 4th divided by 9, which would be a positive quantity, and that makes our argument a positive quantity. So the product property of logarithms had to be used first. Natural logarithm has a base of e, so we'd have e to the 4th power equals the 9x, and then from there. Let's try this next one. All right, so hopefully on this one you got a valid solution of 20. We, with the plus sign there, have to start with our product property, so we have to distribute the 3 to the x plus 7, giving us a new argument of 3x plus 21. Then we rewrite our equation in its exponential form so we can continue solving for x. All right, let's see. Let's go ahead and give this one a try. All right, so in this one, we have a natural logarithm equals a number, so we have to realize we have a base v for that natural logarithm. So hopefully you just went right to exponential form, used some algebra to solve for x. And again, e to the 9th power is going to be a very large number that's positive, so subtracting 3 is not going to change that, and then dividing by 5 it'll still be positive, and then multiplying by 5 and adding 3, make sure that it will be positive. All right, that will end this lesson, so you should be able to begin your assignment.